Hey, welcome to a continuation on our discussion about exponentials. So I first wanted to start off this video talking about evaluation of exponentials. So let's say we have the function f of x equals 2 to the x. Now, there's a whole bunch of values that we would have no trouble evaluating this at. So f of 1, we know we're just going to plug in 1 where x is, and we get 2 back. F of 3, that's 2 cubed. And we just cube 2, and we know that that's 8. Even f of a half, that's 2 to the 1/2. But if we remember when we raise a number to a fractional power like this, this is just the same as saying the square root of 2. Similarly, f of 1/3 is just the cubed root of 2. Now there's some numbers can be trickier to evaluate. The first type is fairly straightforward. It's when we have a fraction. So if we have f of, say, 5/6, that's going to be 2 to the 5/6. And what this means is that we're going to take the 6th root of 2 to the 5th. So all we do is we take 2 to the 5th and then find the 6th root of it. Now, the only tricky things with evaluation is how do we actually find the 6th root? Well, that's a discussion in like computational math, but we're comfortable with having 6th roots or whatever and just leaving it in that form. An even trickier case is when you have something like f to the pi. So the trouble with pi is that pi doesn't have an end, and we can't represent it as a fraction. .1415 and so on, and can't represent as a fraction. Now, if we could represent it as a fraction, it'd be easy. We would just do what we have above. The f of the 5/6, we would instead put in the fraction for pi and just do that. But pi doesn't have a fraction, so we can't do that. So instead, what we can do is we can take approximations of pi. So, and use fractions that way. So one thing we have is that pi is approximately 314 over 100. So then 2 to the pi is going to be close to 2 to the 314 over 100, which is the 100th root of 2 to the 314. All right, so mathematically, this is a nice way to do it, where you can just get an even better approximation by doing 2 to the 31415 divided by, now we need to bring it back down to being 3.14, so 10,000, and that's a better approximation. All right, computationally though, this is useless. I don't think there's really a calculator that will ever calculate 2 to the 314 exactly. You can try it on Wolfram Alpha, and it will probably either give you an approximation or shoot you an error. And then taking the 100th root as well is hard. But the point is that we can do it. And then there's a whole branch of math called Numerical Analysis that discusses better ways to approximate something like 2 to the pi in a way that a computer can do it really efficiently. So that's something that if you're interested in this, you could look into in the future. But yeah, so our takeaway here is that we do have a way to evaluate 2 to the pi if need be. For this class, though, it will always just suffice to just leave 2 to the pi as 2 to the pi. We don't need to worry about evaluating it. And maybe we should note that 2 to the pi is also pretty close to 2 cubed. So if you want to think about what 2 to the pi is, we can think about it as being a bit bigger than 8. So I'm not sure what it is. Maybe it's 9, but because it's 3.14 and 2 to the 3 is 8, 2 to the pi is going to be a bit bigger than 8. All right. So now we're going to discuss a new number that I don't know if you guys have heard of before. It's the number e. E is a number like pi in the sense that it also doesn't have a decimal, a truncated decimal form. It doesn't have a fraction form. It goes on forever with no repeating pattern. But it's important for these exponential models. And we'll see why in a short example. So we've had our COVID example. And let's alter this COVID example a little bit. Let's say that we have, instead we're going to start with 1 person infected. And we say that an infected person infects 1 person a day. All right, so just choosing these numbers is going to make our computation a little bit simpler. All right, so our goal is to find a model that will say how many people we have infected on another day. And we would know that then we have, from our previous work, our model would look like f of n equals 1 plus 1 to the n. Or, I guess that'd be 2 to the n minus 1, so it'd be 2 to the n minus 1. But for now, let's actually start at, let's say we're indexing at day 0, so it's really just 2 to the n. Okay, so maybe we want to think that this isn't the best way to do it. If a person can infect 1 person a day, then this should be the same as it's possible that they could infect the person in the morning, or they could infect them in the afternoon. So we ask, what about half days? So if we were looking at half days, then f to the n equals 1 plus, there's the probability of 1/2 that they get them during any time, during either the morning or the afternoon. So then over the course of a day, we've really had 2 periods go by. So this exponent doubles. So this is now saying that we've broken up the day into 2 pieces. Maybe it's even better to break it up into, we'll say, split day into k pieces. So now we have 12 a.m. over here, 12 a.m. And we're thinking that we're going to split it up into a bunch of little pieces. So I know the drawing doesn't look like it, but we're going to pretend that each of these intervals are the same width of 1 over k. And we have k intervals all together. So we're thinking about k as some giant number, so maybe like 1,000,000. And we're saying that, and we're looking at the probability that we infect a person in that interval. And that would be 1 over k. Yeah, we're still doing the assumption that you're not like sleeping or anything, so you're equally likely to get them between 12 a.m. and to 12 a.m. So then what you have is that f of n equals, for each day, we would have 1 plus 1 over k, k to the n. So we have k intervals, the chance of getting someone in that interval is 1 over k. So it's pretty unlikely that you get it in any one interval, but across the whole day, you're guaranteed to get someone. And the reason we want to do this is that if we infect someone early here, then they're infected, and then it's like we already have 2 people infected at this period of time. So our model adjusts for that possibility that someone else got infected. All right, so now we're going to rewrite this. So we have this, which is 1 plus 1 over k to the k to the n. And for large k, maybe we ask, what is 1 plus 1 over k to the k? And that's actually approximately 2.71 on and on forever, which is our fancy number e. E actually doesn't get its name from exponential. E gets its name because it's called, this is pronounced Euler's number, who was a German, I want to say, mathematician, around the same time as, like, I think we've talked about Gauss and Sophie Germain. So he's around that era, and he was investigating growth models like we're doing now. He was looking at things whose change is directly equal to the size that they are. And he found that there's actually this it's nice that there's a number e that captures it. So what we do is then just replace our model with f to the n equals e to the n to say how many people are infected on each day. And that's that. Yeah, it's a little confusing that this E came out, but essentially the idea is that we're looking at how it changes as we look at more and more intervals of time, because it's taking into account the fact that you could infect someone like early in the day, and then that person could go out and start infecting people. So if you started the day at 12 a.m. and you're the only person infected, but around 3 a.m. you infect another person, so then there's two, then that gives enough time in that day for that second person you infected to also go infect someone between that hours of like 3 a.m. and 3 a.m. the next day. So maybe by the end of the second day, or even the end of the first day, you could have 3 people infected, even though we're saying that you're only going to infect one person a day, because that second person could go out and infect someone else then. So that's why we need this number E that's going to be slightly bigger than just this 2 to the n growth rate. All right. I think I'll post a video on graphing, on approximating E with Desmos in terms of this function 1 plus 1 over k to the k. And then we'll work on graphing exponential functions. All right, see ya.